Next problem, number 72, we're given a horizontal bar from which we're hanging two current carrying wires hanging by a thread. We're told that they are separated by an angle of 16 degrees. We're told that they are repelling away from each other. And then we're asked, does the direction of the current for this one equal the direction of the current for this one, or are they opposite? Well, if we draw a current carrying wire here, let's just do this, and a current carrying wire here, and let's say that this current is going in this direction, and this current is going in the opposite direction. Let's just say this for now. So we use our right-hand rule. Our thumb points that way. That's going to give us a curl of a B field this direction. And if we point our thumb this way, that gives us a curl of a field this direction. So these fields are going to create a force that repels away from each other. If they were equal and opposite, they'd cancel. If they're not, then they're going to repel. And that's what we have. Wait, that's not quite true. This part is true. They wouldn't necessarily cancel. Not necessarily. But in this case, they're repelling against each other. That's the main point, right? So, okay. So we're asked now to find the currents. What are the currents of from the wires, right? So what we have is we have a string with a weight attached to it. So this is going to give us a tension force. This is going to give us a weight force, right? So we have a tension force, we have a weight force. We also have an electric force separating these two things. So let's set up a force diagram and consider these things are in equilibrium. So this is a cross-section view, right? This is the first cable and wire. This is the second cable and wire. We're told this whole angle here is 16 degrees. Why is that? Nope. Okay. Well, anyhow, this whole separation is 16 degrees. So that means that this angle is equal to this angle, and those angles are 8 degrees, right? Because we have an entire separation of 16. Okay, we also have a tensile force pulling this direction, so that means that we're going to have a y direction. Sorry, it's going to be going up for tension, and then we're going to have a x direction for tension. We have a weight force in the y direction. We have a separation force, right, for an electric force. Or we have a magnetic force, actually. Sorry. So okay, so let's do the y direction. So F in the y direction. We're saying these are stationary. They're in equilibrium. This is going to equal 0. Now we have Fty plus weight force is equal to 0. We already wrote that down. So what is that going to be? So this direction here is actually, since our angle is over this way, is going to be, if I can get this to work, it's cosine of the angle. So this is the magnitude of the tension force times cosine of the angle, because it's pulling upwards, right? And that's cosine 8 degrees. And then the weight force is pulling in the downwards direction, so that's negative m times g. So that gives us that, the tension force magnitude is equal to mg over cosine 8 degrees. Now let's take the x direction, also in equilibrium. We have a tension force pulling to the right. We also have, if we just pick a direction, right, we also have an electric force or a magnetic force pushing to the left. So that means that we have, it doesn't really matter which direction you define them to be because they're in opposite directions and we're in equilibrium. So what we're going to end up with is ftx plus f magnetic equals 0. And so then that gives us the magnitude sine of 8 degrees, right? Sine 8 degrees minus, then we're going to write this down as minus FB. And then so we're saying that the magnetic force is going to be equal to, if I can get this, Ft sine of 8 degrees. And that is because we already found what this value is, cosine 8 degrees under mg times sine of 8 degrees. And that gives us mg tangent of 8 degrees is equal to the magnetic force. We also know that this magnetic force is going to be equal to the magnetic field strength times the current times the length of the wire, right? Times the separation, times over 2 pi r, which is the separation distance. This is also going to be, because we can open up the magnetic field, right? We have over, this would be sine of an angle between them, which would be 90 degrees for this case. So the magnetic force is equal to mg tangent 8 degrees, and that's equal to b times I times L, right? If we open up the magnetic force, then we have 2 pi r, then times the current times the length. Okay, so that's what we're after here. And so now we have mg tangent 8 degrees equals mu naught over 2 pi r I squared times L. We want to solve for I. No big deal. I is equal to the square root of mg tangent 8 degrees times 2 pi r, which again, this is the separation distance between the interacting force. Mu naught over L, that's the length of the wire. This is the length of the cable, sorry. What I mean is, we're told this length. So this is the this is the L. This is L. That's what I'm trying to get to. L. This is R. Okay? So then we just plug everything in. Oh, but there's a problem, and that problem is, we don't know the mass. And when I said that this is L, sorry, that is also a mistake. Because we're talking about a magnetic force coming from a current carrying wire, we're talking about the length of the wire, right? We're not given that information, but we are given a density, which is mass over length. That's what we're given. So ignore what I just said about that earlier. We are given that, I believe, but we don't need it yet. We don't need it yet. We will in a moment, but not yet. Okay, so because we're using the force from a current carrying wire, we're using the length of the wire. That's what L is, right? So going back down here, noticing that we have M over L. We were given M over L in the beginning, and that was 0.04 kilograms per meter. That's a density that we're given. So now we can just plug that in. So I is equal to 0.04 kilograms per meter. Tangent 8 degrees. Then we have 2 pi. We don't know what R is yet. 1 over mu naught. So R. What is R? R is the separation distance between the two interacting current carrying wires, right? And if we look at our force diagram, we really just need to figure out what is this distance and what is this distance, because this is going to be R. Okay, well, we were told in the beginning that we were given a value for this length. So what we're going to have is we're going to have a factor of 2, because we have 1, 2, right? Times the length of this cable, the length of this wire, call it L, times sine of 8 degrees, which is going to give you this length here. So that's 2 times 6 centimeters. We're told that. Otherwise, 0.06 meters, sine of 8 degrees. And that gives us a value of 0.0167 meters, or 1.7 centimeters. Okay, so that's our value of R. So we take that and plug it in. 0.017, we'll say. Okay, so now we have everything. We have this, there's nothing missing. We know this, this, and we plug it all in. We end up with 67.82 amps. That's what I got. If you have any questions on this, please feel free to email me. As always, I went through it kind of quickly, and I did make one small error earlier. I just like to reiterate that L, that curly L, is the length of the wire, right? We're told the length of this cable is 6 centimeters. 6 centimeters here. This is L. And what else? There was another one. Oh, this is R. That we called little r here. Okay, so there were 3 lengths to consider. All right.